Chapter 1. The Scale of the Challenge. Before we talk engines and starships, we need to talk distances. The nearest star system, Alpha Centauri, is about 4.37 light-years away. At the speed of today's fastest deep space probes, that's tens of thousands of years. Voyager 1, the champion of fast from the 1970s, is doing approximately 17 kilometers per second, about 0.006% the speed of light. At that pace, reaching even the nearest star is effectively never. The conclusion is blunt. Interstellar travel demands radical propulsion and mission design, not incremental tweaks. Chapter 2. 3 Pathways to the Stars. Across the research community, 3 broad strategies repeat. 1. Ultrafast robotic probes, small, lightweight scouts that reach a significant fraction of light speed. 2. Slow but sustainable crewed ships, world ships, hibernation missions, or modular habitats optimized for centuries. 3. Physics-heavy wildcards, beamed propulsion, fusion, antimatter, and theoretical ideas like warp metrics. The first path will likely happen first because miniaturized probes are easier to push to extreme speeds and survive the trip. Chapter 3. Sailing on light. Solar sails that already fly. Sailing on photons is not science fiction. It's already been demonstrated. JAXA's Icaros flew in 2010, deployed approximately 200 square meter sail, and verified both photon-driven acceleration and attitude control using liquid crystal panels embedded in the sail. The Planetary Society's Light Sail 2, 2019 to 2022, then proved controlled solar sailing in Earth orbit before re-entry in 2022. These missions were slow compared to interstellar speeds, but they showed the core mechanic works in space. Chapter 4. Laser-driven sails, pushing to 20% light speed. Replace sunlight with directed energy, a phased array of high-power lasers, and momentum transfer skyrockets. Physicist Philip Lubin outlined a roadmap in which wafer-scale spacecraft riding ultra-thin sails could reach greater than 0.2 C with ground-based laser arrays in the 10 to 100 gigawatt class and advanced optics. In 2016, Breakthrough Starshot popularized a similar concept. Gram-scale probes with meter-class sails, pushed to approximately 20% light speed, fly past Alpha Centauri in approximately 20 years and beam images home. Technologically audacious? Yes, but rooted in physics we already understand. As of 2024 to 2025, Starshot's leadership has openly said the program is on hold, largely for cost and infrastructure reasons, while work continues on nearer-term directed energy applications. The concept remains a serious line of research. The institutional push is the part that's paused. Chapter 5. The Invisible Minefield. Dust, gas, and 0.2 C at 10 to 20% light speed. A grain of dust hits like a bullet. Peer-reviewed studies of relativistic spacecraft in the interstellar medium quantify erosion depths, melting of surfaces, positive charging, and magnetic deflection. Design responses include sacrificial erosion shields, beryllium or graphite-based, Whipple-style multi-layer bumpers, leading dust clouds to pre-vaporize particles, careful trajectory planning through lower-density regions, and active attitude control to keep the toughest face forward. If we want probes to arrive intact, shielding is as fundamental as propulsion. Chapter 6. Fusion Rockets, from Daedalus to Today. In the 1970s, the British Interplanetary Society's Project Daedalus designed a credible, uncrewed fusion star probe. Using inertial confinement micropellets of deuterium/helium-3 ignited at hundreds of pulses per second, Daedalus would accelerate for years to roughly 12% light speed, cruise for decades, and deploy subprobes during a high-speed flyby. No deceleration. Daedalus wasn't a paper fantasy. It was a detailed engineering study that set a baseline for fusion starships. Huge mass, complex fueling, extreme power densities, but within the bounds of physics. Chapter 7. Direct Fusion Drive. Compact fusion with power to spare. A modern line of fusion propulsion research centers on the direct fusion drive, DFD, based on Princeton's field reverse configuration, PFRC. In DFD concepts, a compact reactor, order 1 to 10 megawatts, produces both thrust and significant electrical power for instruments and high-bandwidth comms. Lab and modeling work continues. Mission studies envision fast outer planet missions and, eventually, interstellar precursors once performance scales up. DFD is not flight-ready, but it's a promising path that merges propulsion and power into one engine. Chapter 8. Nuclear, Thermal, and Electric. Fast Solar System. Foundations for Interstellar Nuclear Thermal Propulsion, NTP. A fission reactor heating liquid hydrogen offers 2 to 3 times the efficiency of state-of-the-art chemical rockets and is ideal for rapid Mars and deep space missions. NASA and DARPA's Draco demo, planned for 2027, was placed on indefinite hold in early 2025 due to test and regulatory hurdles. The technology case remains strong, but flight demonstration timelines are uncertain. Meanwhile, ion and Hall electric propulsion have logged millions of hours in space, moving probes with exquisite efficiency, excellent for building the infrastructure, relays, depots, telescope arrays, interstellar projects will need. Chapter 9. Beaming Power versus Beaming Momentum. A key design choice is what the laser array provides. In laser sail systems, it provides momentum, pushing directly on a reflective sail. In laser electric concepts, it provides power to a distant craft via photovoltaics or rectennas, which then drives its own high ISP thrusters. Both approaches live under the umbrella of Lubin's Directed Energy Roadmap, and both depend on building scalable, phase-locked arrays with adaptive optics and precise tracking. The payoff is enormous. Tiny probes at relativistic speeds, and later, larger craft at thousands of kilometers per second. How to stop? Braking without carrying fuel. Go. Going fast is half the problem. Stopping at the destination is the other half. Strategies include photon braking / photogravitational assists, using the target star's light pressure and gravity to shed velocity with careful sail choreography. Magnetic sails, mag sails, carrying large loop fields to interact with stellar wind or interstellar plasma for drag. Hybrid mission design, a swarm where some probes perform flybys, fast data, while a few larger, slower craft carry propellant or deploy mag sails for capture. Today's consensus: flyby first, capture later as technology matures. Chapter 11. Navigation and comms across light years. We can't take GPS with us. Instead, spacecraft can navigate using pulsars, ultra-regular cosmic lighthouses. NASA's Sextant experiment on the ISS demonstrated autonomous X-ray pulsar navigation in late 2017, achieving on-board, real-time fixes by timing millisecond pulsars. For communication, high-gain laser links and relay assets, deep space telescopes, perhaps even solar gravitational lens relays someday, become crucial. Power-rich propulsion like DFD also helps by supplying watts for big transmitters. Chapter 12. Keeping Humans Alive. Habitats, Loops, and Shields. For crewed missions, propulsion is only the start. We need closed-loop life support that recycles air, water, and nutrients nearly perfectly. Radiation protection using water, polyethylene, and habitat design, and biological/psychological architectures for decades-long voyages. Rotating habitats for gravity, greenhouses and bioreactors for food and oxygen, and in-transit maintenance factories for spare parts are all on the critical path. Hibernation, torpor research is ongoing, but we should plan as if robust, regenerative ecosystems are mandatory. Chapter 13. Mission Architecture, From Precursors to Full Scale. A realistic interstellar program might unfold like this. 1. Interstellar precursors. Fast solar system exiters to 200 to 1,000 astronomical units, using advanced electric or nuclear stages, mapping the outer heliosphere and local interstellar medium while validating nav/com. 2. Beamed sail demos. Earth-Moon laser links powering microsails to tens of kilometers per second. Then cislunar to interplanetary trials. 3. First flyby probes. Gram to kilogram craft to Alpha Centauri. Fast science, test shielding, and downlink. 4. Capture-capable systems. Mag sails, photonic braking, or fusion stages for in-system operations. 5. Crewed infrastructure. Only after years of robotic logistics, fuel cycle mastery, and closed-loop biospheres. Chapter 14. What success looks like in our century. Interstellar travel is not one finish line, it's a ladder. This century's likely wins, sending tiny laser-pushed probes to nearby stars, building the directed energy infrastructure that also boosts planetary defense and power beaming, fielding faster fusion electric deep spacecraft, and pushing life support toward true circular ecosystems. Each rung makes the next possible. The dream is intact and the roadmap is clearer than ever.